Hello, everyone. Today, I'm going to talk about the modern medical image segmentation, automated machine learning, and beyond. My name is Dong Yang, and as Dr. Zhao introduced, I'm from NVIDIA as well as an applied research scientist. And thank you guys for having me here. This is today's agenda. So firstly, I will talk about the modern medical image segmentation. And then I will cover the topics of automated machine learning in medical imaging. Then I will talk about some related topics based on the medical image segmentation. Okay, let's jump right into the topic. So, as we all know, the goal of medical image analysis is to gain high-level understandings from the medical images, and we could apply it. Okay, so as we all know, the medical image analysis is mainly to gain high-level understanding from medical images. So it could be used for disease diagnosis, treatment planning, and surgery guidance. So we have tons of applications for like accurate radiotherapy or like potential like COVID-19 screening from chest X-ray or chest CT. And we do have a lot of like applications like you can see like we have segmentation, classification, detection, and other applications in medical image analysis. And the image modality could vary a lot, like CT, MRI, chest X-ray, a lot, as you can see on the list. And the question we are trying to answer here is trying to find out the optimal relationship between the clinical expertise and the artificial intelligence. Okay, this is like I make a summarization of the MICAI 2021. Like I put all the titles into this like statistics, and the font size indicate the frequency of this word appearance in these titles. So it turns out once you summarize all the information together, these three words stands out like specifically. Firstly, segmentation. Second one is deep, and the last one is learning. So which means like the segmentation is kind of one of the most popular tasks in medical image segmentation. And the people tend to use a lot of like deep learning based approach nowadays to resolve different various applications in the medical image analysis. So that's also one of our motivation to dive into the segmentation application specifically. So to be like more specific, like for example, the 3D medical image segmentation is like a given 3D volumes like CT, MRI as input. We're trying to parse the 3D structures of organs, tumors, or bones. As you can see from the following 4 figures, we are trying, like the example shows the segmentation of the left atrium, the right atrium, and the segmentation of liver and the liver tumor. Here are some nice rendering results. And now I will talk about a little bit, talk about the history of the modern medical image segmentation. So segmentation in terms of formulation, there's like several, there's mainly I summarize as a 2 parts. Firstly, like a segmentation, basically we're trying to predict the segmentation mask. So mask basically show you like the inside the mask is a region of interest you want to segment, and outside the mask is like a background you want to that's not your interest. So first work is like really like a long-term goal is like a graph cut. So basically the graph cut formulates this like using the image structure forming a grid, then use a grid to do some like max flow min cut optimization, then find a segmentation from the 2D or 3D medical images. And next one is the random walker. Similarly as a graph cut, and people are using like a grid like naturally from this 2D image or 3D images, and use some like priors like background or foreground as this like scribbles. Then based on this, the algorithm will figure out the probability of each pixel to be foreground or background like automatically like smartly, then do the segmentation task. And the next one is deep learning. So nowadays, deep learning is heavily relying on this kind of formulation to segment the mask from the image directly. I will talk more about this in following slides. So the second framework here is like trying to segment the contour or surface of the region of interest from the images. So first, like famous work is like SNAKE, is an active contour model. So you form some like energy formulation and use a gradient descent to to minimize the energy. For example, here from the figure you can see if like an initial point is here with the initial curves. So once you start to minimize the energy, the curve start to fit into the boundary of this pier. Here you can see then once like the energy becomes like a global minimum, then segmentation is kind of achieved. And secondly, is similar as the SNAKE, is people are using the deformed model. So for this work, and people propose another kind of like additional energy constraint based on the gradient vector flow. So still like using the active shape or active contour models, and people can get a better segmentation using this like DVF. And also other researchers trying to apply some like physical modeling here and trying to help to make a better segmentation inside of medical image domain. And the next one is level set again. So it's also like very similar like formulation, still like a minimize using a optimization formulation to minimize the zero level and of this function, and trying to this zero level actually indicate the boundary of surface of region of interest. And the next one I'll talk about this marginal space learning. So it's kind of like an innovative way to do medical image segmentation, and especially in 3D, like during that time, like 2008 or 2006. So this is kind of quite powerful tool. Like people, like researchers from Siemens, like they are created this algorithm. They have three like estimators to estimate position, orientation, and similarity translation. So based on this three estimators or detectors, it can detect region of interest first, then using some non-rigid deformations and form the shape prior towards the targeted locations and achieve a very nice segmentation. Here you can see there's like a 4-chamber hard segmentation from 3D CT. So nowadays, with great advance of hardware and also like algorithm, so deep learning become more and more popular in almost all possible applications in medical image analysis, but also like computer vision. So one big reason is it has greatly improved performance. For deep learning in segmentation, there's a few work I want to mention here. The first one is like the fully convolutional network, or FCN. So this is kind of like the starting of this segmentation network since like 2015. So you can see, as I said, it's a formulation is a pixel-wise prediction or pixel-wise classification. So for you have the input and you have the like output is like a 1-to-1 mapping. But for output pixel for each location, you predict like a probability for different classes. Then you choose the one with the highest probabilities and become the class label. Then that's very standard like a formulation nowadays for image segmentation. And the next one is like really introduce the 3D convolution and also like this deep supervision concept into the field in 2016. So the work is kind of, now if you see now, it's kind of a similar like a U shape or symmetric shape, but the really success like of this work is like you can train the really good solid like a liver segmentation model with using only 20 training data. So that's kind of a success in a small 3D data set. next work is kind of popular is like the U-shape or U-net invented by 2015. So it kind of symmetric design of encoder decoder with a skip connection between them and achieve very good decent performance of segmentation in both 2D and 3D medical image segmentation. Beyond that, like recently, this work kind of popular in like several segmentation applications called NUNet. So it basically combine the various like 2D, 3D unit and make an ensemble from all the predictions with very good performance. So you can't. So I think it was like a state of art for many applications, like back in like 1 or 2 years ago. Okay. So to summarize the deep learning framework nowadays, as I showed, like it's like kind of image to image mapping. You do this like segmentation based formulation. Now you have like an image like CT, MRI, like pathology, then you predict the labels on each pixel or each voxel. Then normally we do the data pre-processing and data augmentation for training. Then we select the model we like, the UNet, the VNet, and also like Segmentation and others. Then based on this pre-processing and the model, then we choose our like hyperparameters for gradient descent. I see like what will be the learning rate and what will be the optimizer and the VDK, etc. Oh, and here's I just want to introduce this like a MONAI concept here. So the MONAI is kind of the open source project from the entire field, like KCL, Harvard, and ICL. They are all contributing to this big open source project. We are part of it, and we are trying to create this nice open source project to assist other researchers in the field of medical imaging and to do the like segmentation classification. It has some nice features as I mentioned before. Okay, so based on so now we have the study like a foundation of segmentation we're using deep learning in medical imaging. So now I want to talk about AutoML machine, like automated machine learning here. So the automated machine learning in medical imaging mainly like 3 parts, like you do the hyperparameter optimization. So there's tons of hyperparameters like batch size, pair size, learning rate, VDK, as all those parameters you need to tune. Secondly, data augmentation, data pre-processing, augmentation, post-processing. So how you're gonna do the image normalization. So for example, like in UNet, like CT, MRI, they have different treatment as a pre-processing. And also for the augmentation, because there's a randomness there. You need to control the probabilities of each transform and also other parameters you need to like carefully design. And then the last one is not the least, but it's kind of important topic here is neural architecture search is NAS. It's trying to find the efficient and effective neural network architecture for like 3D or high resolution medical images. So from our team, like what do we have done in AutoML so far? So we have been working on this topic for a couple of years. So firstly, we introduced this concept called VNAS. Like it's kind of first work ever in using neural architecture search for like 3D medical image segmentation. So the concept is using the differentiable architecture search. Basically, we are trying to. This is like all the potential connections between different nodes. The nodes, you can consider them as a feature maps. And during searching, we are trying. There's a weight along with each possible connection here. So during the searching, we are trying to not only optimize the model weights, but also optimize the path weights. So once the path weights is optimized, after like searching, we can binarize them and extract the final architecture from this like all the candidates. That's the ultimate algorithm here. So here we're using like the U-shaped structure and search for the operations at different level or different positions. You search for like 2D or 3D convolution, or like this called pseudo 3D convolution here. And as I said, there's a two-part model. Like during the searching, there's two part of like weights we need to optimize. Firstly, the model weights by itself, the convolution weights, and also there's a path weights we need to optimize as well as alpha beta here. So we alternatively update two sets of weights, and eventually we achieve the final architecture with argmax. And here's some number. Of course, once we apply this searching strategy on top of like the plain UNet, we will achieve like kind of convincing result. So in 2019, so we created this reinforced learning based controller concept here. But it's mainly for the hyperparameters tuning. It's kind of straightforward. Basically, you have the initial state of all the hyperparameters, like the probabilities or learning rate. Then you have trained the agent, the RN agent, the controller agent. So each time the agent takes the state, like state, which means like all the current parameter combinations, and take the actions. The action will give you the new set of parameter combination. Then iteratively, you will give you better like hyperparameters for model training. And the reward for this reinforcement agent is validation accuracy here. And again, so we apply this based on the some like baseline using the similar framework, but just like different hyperparameters. Eventually, we achieve the better performance comparing to the baseline. And in 2020, so okay, so now we think maybe we can think something more beyond the U-shaped network in terms of neural architecture search. So we created this method called the C2F-NAS. C2F-NAS is like the course to find neural architecture search. But mainly this is like the two part we want to searching for. This one part is like the global architecture. So we want to see is there possible we can find some like architecture is asymmetric but with good performance. And also the operation also want to optimize. So we want to see whether this convolution is the best, or we want to see 2D is the best, 3D is the best, or like a P3D is the best. So that's all the combination we want to look, we look for. And there's two stages. As you can see from the figure, we have the grid as a searching space. The searching space, that means like it contains tons of the possibility of the network connections. The U-shaped UNet is also could be part of it, just like as a U in this grid like space here. So we use the evolution algorithm here to search like for the best network here, and then we define this like in the core stage search. We're trying to define the course global structure of the model here. And in the fine stage, so we're using this like a single pass one-shot NAS to determine the operation like 2D, 3D convolution at each node in this like a global within this global structure. And we evaluate our algorithm search model on this like large scale medical image segmentation challenge or data set. Is available online nowadays, still available. Public leaderboard still is active right now. It contains 10 different segmentation tasks, including both CT and MRI, and also organ and tumors. So during that year, 2020, so the C2F-NAS was state of art for that challenge, and we kind of like outperform all the like participants, including UNet and other entries. Okay, in 2021, so we introduced this things concept. It's a kind of a newer state of art of that data set in 2021. The question we are trying to answer here. So, okay, so in C2F-NAS, you can see where can search for the single path network within this grid-based searching space. So how we can search like the multipath? Maybe multipath give us more benefit here. So we are introduced this algorithm. It can do the flexible multipath search, and we introduce some topology guaranteed discretization algorithm. And also we have the nice feature of it. It's like we're trying to add this memory budget constraint into loss function. So once you tune this like parameters like the sigma here, then the outcome, the search model will with different more or less memory consumption that you can control. So you can see based on this different sigmas, this is like the number here is the GPU memory consumption. So basically you can see it with different numbers of the control parameters here. You can see the network from the searching algorithm, searching process will be difficult. Will be different. Okay, so in that year, like 2021 is like the first entry of the medical images decathlon challenge. So it kind of outperformed C2F NAS in almost all tasks. And another benefit of this approach is kind of like using like less than 200 GPU hours, and comparing to C2F NAS, which is using 8,000 GPU hours to do the searching. It's kind of like a big step, like moving forward. And now we open source this like a DINGS algorithm on the based on the inside of Monet repository. So if you're interested, feel free to try it for your application. You can use it for both 2D and 3D segmentation tasks. Okay, so this is like four like milestones we achieved like over the last 4 years. So what's more work based on these studies? So there's a few more work I just quickly cover here. This is like we applied the neural architecture search under the context of federal learning. So this paper published in the MICAI last year, and trying to figure out what would be the best architecture for for each client, because like as we all know, the federal learning. So different client has different data, but the data itself is not shared across different clients. So they may have like a domain shift between different clients. So neural architecture here trying to adapt the like best candidate operation for each client in order to achieve like a better performance. And another work from last year is MICAI is like a proxy data and a proxy network. So the concept of proxy here, because like as I would say, the regular AutoML or neural architecture search algorithm takes a lot of time to do the training. Normally, like you need to train like a thousand of like instance or training jobs to achieve like a very robust like searching outcome. Then this study is mainly to reduce such like a searching cost. So either there's two ways we can do it. The one way is using proxy data set, which means we use like subset of the entire data set to do the searching. Another way is trying to using like the smaller network to do the search for the hyperparameters. Then we apply to the like a larger network and also larger data set. So then we come to this like the one of the main topic of this talk is called T-AutoML. It's published in ICCV last year. It's trying to search all possible components in deep learning. So the contribution has a multifold, and trying to propose a predictor-based AutoML algorithm, and searching on the reasonable budget, like 300 GPU hours, still reasonable comparing to 200 GPU hours like in DINGS. And also we propose this efficient predictor training algorithm and flexible architecture design. So that's a question we found out during our study, both in the literature and our study, like the searching for the components, like individual components, may lead to suboptimal solutions. So from this CVPR paper, we can see like even with same RESTnet, like this RESTnet 15, the recipe here means like different set of hyperparameters. If you use a different like a recipe, the performance will be different, even you're using different networks. So which means like neural architectures may have some limitation there, because you change the training scheme, then you definitely get different ranking across different networks. So that's why we come up with this like idea. Okay, so maybe we can jointly search all of them, like a neural architecture, data augmentation, hyperparameters, loss function, optimizers, everything together. And another the task we are trying to tackle here is the lesion segmentation within like 3D city. Sorry, the lever and the lesion segmentation. You can see the challenge of from this appearance. You can see both like the weight boundary of lesions and also appearance difference across different CT scans. And what can we learn from those recent literatures? So this is like the work from Google, like published like 2 years ago. For they call SpyNet. The SpyNet is really trying to find this like arbitrary connection between blocks for object detection task. It kind of give us like, okay, so maybe this kind of design, like symmetric design, kind of meet intuition, is simple, it's nice, but maybe we can do this arbitrary connection, which gives us like more benefit. And another work is called Hypersoft. This is from Microsoft. It's also same year CVPR from Microsoft. So the idea behind this is like trying to use this like hyperparameter as part of input, and together jointly training with data and the data set, and using this information predict the performance of each hyperparameter configuration or recipe. So based on the predicted performance, then you can choose the which configuration you are going to use. But the nice thing for this predictor concept is like you can apply it for the unseen data set. Then you directly can rank these recipes and choose the one you like, the model like best to do the downstream task. And another work on the next one, as previously architecture and hyperparameters, and this work, okay, really start to rank all the components together. So what it did, like it kind of like a combined architecture and label and dataset ID, kind of just ID and hyperparameter into this fully connected layers to predict the performance of the model. Then using this predictor, then you can predict use them can do the ranking here. And the next one, the next very interesting work is published like Europe's 2 years ago. It's like kind of doing this comparison. So they still do the neural architecture search, but instead of doing like predictor, they're trying to use it to network as an input. Use is kind of like a Siamese structure, and as input here and predict which one is better. But this is mainly for neural architecture search. So with all those like advanced in the field, but how we're going to apply it to the 3D medical image segmentation context here. So what to optimize? So AKA the searching space. So we are trying to incorporate all the advanced here. So we do search for the architecture augmentation, especially which augmentation to use, and the hyperparameters, loss function of optimizers. For neural architecture, similarly like a SpyNet, we want to achieve this like a nice arbitrary network structure and arbitrary connection between layers. And we're searching for 2D or 3D convolution or 2D, 3D actual attention module. I will show it later. And also, unlike in the other network literature, the U-shaped structure is less favored in our experience under this context. Okay. So here's a like actual attention network, module. So basically, as we the kind of as we all know, so computing the attention within the entire image domain could be like very expensive. So especially for 2D or 3D images. So the researchers are trying to increase this like a one-dimensional self-attention along each axis to reduce the burden of the computation. So here in their original work, they are trying to compute attention in X and Y axis separately. But in our context, we add additional like axis as a Z axis because we are dealing with a 3D medical image. So that's kind of like an actual attention module we use in our framework. And what to predict? There are two things we can predict. First thing is accuracy, and the second thing is the relationship. As I said, relationship just like to compare which configuration is better, which one is greater, which is less. So we do this input and augmentation, loss function, optimizer, hyperparameters, all of them encoded as a very long vector. So for each part, we predefine like a larger search space as a like vector. For example, for architecture, we are trying to make a like one hot encode vector for it's like a binary encode for architecture as an input. Similarly for augmentation and for the hyperparameters, it could be floating numbers here. And then we need to train this kind of predictors. So we really need a lot of ground truth to do that. So let's say if we have an training job, give us like 10 different validation accuracies. So if we train the accuracy predictor, then we can have own n data points for ground truth. But if we train the relationship like a comparison predictors, actually we have much more ground truth like in a higher order. So which means like the model with like kind of relationship like predictor kind of will be more robust given the limit ground truth data points. So we use this like a relationship kind of based the predictor, and once the predictor is trained, we do the sorting here with sample n configurations. We can use the standard sorting algorithm to rank different configurations and pick top M configuration and retrain and fine tune them. Then after fine tuning or retraining, then you choose the one with the highest validation accuracy as a final model and a final checkpoint. So this is like a network we searched from using this algorithm. So we compare with other like established network, SegNet and the 3D UNet plus. They all kind of like symmetric design, will kind of meet a human intuition. But this network from our model is kind of, you see, it's really hard for human to come up with this kind of architecture to do segmentation, but it works really well. So we are tested on this like a public challenge called the LEADS, Liver and Tumor Segmentation Challenge. So it's public, it has been public since 2017 with more than 3,000 entries here. And on the left-hand side, we made entries to the public challenge. We still have our entry there. So our entries kind of like outperformed all the published work in the past with a higher like lesion or liver like segmentation in terms of a higher accuracy in terms of the DICE score here. And also, so we searched from the data set, and then also we transfer our search network in another data set called like MSD lung tumor segmentation. Lung tumor segmentation in MSD is a really small data set. It has only like 40 data points. So we just retrained the search architecture on this data set. Still, we reach a very good performance on the number also still from that like a test leaderboard. It's kind of like encouraging for us. And And also, we show this like comparison between the accuracy predictor and the relationship predictor, and also we introduced this like a transformer-based predictor. So since we are dealing with the one-dimensional vector as the input, so we can use the transformer to do the predictor as well. So comparing the correlation between ground truth rank and the predictor rank, we can see this kind of relation-based, not only plain relationship between space the predictor or the transformer-based relationship predictor. We all got like quite a reasonable correlation between the ground truth and prediction. But for accuracy predictor, actually within like we only have a few like 25 like data points to train here. You kind of see that we don't get like any positive correlation between the accuracy. But for relationship, yes, we can definitely get a good correlation there. And then we also compare some computer error other metrics like Kendall-Tall and Spearman correlation. Sorry, anything? Any question? Okay. Then next we compare the model. The first model actually has like a smaller model size comparing to the standard UNet or UNet++ or C2-NAS. Here are some like segmentation results. Like first row, it shows segmentation result for the liver and the tumor segmentation in 3D CT, and the second row shows the segmentation of the tumor, lung tumors from chest CTs. And yeah, the one major contribution of this work is kind of like this predictor-based AutoML algorithm is able to cover all the possible components, and we are searching under like a reasonable budget, comparing to things only search for the architecture. So what's beyond AutoML? So because like we think like medical image segmentation is kind of important topic in the field. We are trying to review the problem in different perspectives. For example, this work that recently accepted at CVPR 2020. So we are trying to incorporate the popular transformer-based modules or like established like a swing transformer here and incorporate into this like a U-shaped structure, make it like a more powerful segmentation network for segmentation task. So and also we enable the pre-training training for this model. We pre-train this on the model on the largely available CT image without any label. Then we fine-tune on a downstream task which can achieve state-of-the-art performance on MSD and also another challenger called BTCV. So both are like still the #1 nowadays on the leaderboard. And the swing UNet are kind of use 3D shaped window for self-attention computation. And the formulation is like trying to do this like a patch-based encoding, put it into the swing transformer encoder, then do and for the downstream task or like for the like a pre-training. Here's some like a detail for architecture. You can see the kind of we incorporate into the encoder part, and for the decoder part, we use a regular convolution to achieve the final segmentation result. And this is the work trying to see whether we can do the active learning with medical image segmentation. So basically, we want to, for in the real context, for doctor or radiologists want to do annotation. They want to, in order to reduce the effort. So in order to reduce the effort, we want to like try to train a model to tell doctor which data to pick, which data to annotate first. Then using the pre-trained model that can do the like the initial prediction, and doctor can easily make changes on the initial prediction and speed up the annotation process. And this one is we're trying to apply this semi-supervised learning under the context of federal learning, trying to do the correlation segmentation. And the last one here is trying to incorporate the chip priors into the segmentation model. Here, the interesting work is like trying to have an initial mesh here. We got like features from this like a segmentation network from this unit. Then we do the iterative refinement of the initial mesh like a ball here. And from the mesh, eventually we reach the shape of lever. Then you become this really interesting work. And combining both mask-based segmentation and also surface-based segmentation, we can further improve the performance here. Okay, so now I will make a summary. It's a lot of contents. So I think it's still like a deep learning is really powerful solution for segmentation in medical image analysis, but still is a lot of challenges because like we see various pathology, tissue, bones, organs all the time. And the annotation for the training data is kind of limited because like, especially for the high quality annotation, it's really hard to get. And sometimes you will see the noise labels because it's kind of common, the disagreement happens between different doctors or radiologists. So somehow we need to handle that situation as well. And also insufficient intelligence. I would say like, even with the most advanced algorithm for segmentation, we still can see the gaps between doctor's annotation and model predictions. There's something the model cannot really think like a doctor. So we need to, that's the room for like, definitely that's the room for improvement. And a potential research direction could be used like, because we have a large available unlabeled data on the internet. So it's better, one promising direction will be self-supervised learning by pre-training with large unlabeled data. And also model interpretation. So you will want to train the model and also model will also tell you why they make such like a prediction. And for AutoML, we have some like just our grand vision, I would say. There are mainly like two visions here. I think it's by explanation. So just trying to explain what are the critical components in the optimal solutions and discovery. So we are trying to find what could be the new things that people didn't know before. That's kind of our grand vision in terms of AutoML here. Okay, thank you. Any questions? That will be all the contents.
Yeah, thank you, Dong. And it's time for questions. If you have any question, you could either like unmute yourself, or you can type on the chat box. Well, I have a question. You introduced,
okay, sure.
You introduced several neural architecture search algorithms, and we
Yep.
know that those NARS algorithms are also existing in computer vision. So, what do you think? Is there any like unique challenge for NARS in medical imaging?
Yeah, that's a good question. So one big challenge from the micro imaging is like we are in most cases we're handling the 3D data. So it is that 3D data not naturally consume like more like computing resources. So there are some like algorithm for 2D image or from computer vision you can naturally apply here because of the limitation of your computing resource. So for example, the GPU memory here is kind of our biggest like concern in terms of neural architecture search. So that's kind of our focus to trying to optimize as a like a additional constraint, additional objective. But in computer vision, I don't think that's really concern. That's really a big concern for them. But for us, it's kind of big objective here.
Yeah, thank you. Yeah, we have a question from the chat box. How much is the improvement brought by the AutoML compared with data itself?
Yeah, I think this is an excellent excellent question. So there's interesting perspectives. So there's an improvement for the existing framework. Like if you have a like training framework pipeline, there's improvement can be multifold. Onefold, you can optimize the architecture you have, like kind of augmentation you have, trying to improve performance, and in another perspective, you can annotate more data. That all increase the quality of annotation, then performance will goes up as well. So it's really hard, like case by case. It's hard to tell, but based on our experience, like both approach can improve your pipeline performance. I think if you have label really large amount of data, then it really helps a lot. But you have like annotated just a little bit, but you have like big searching costs. You have big computing resource to do the searching. Then definitely the part from AutoML will be much larger than the data part. So it kind of like depends on like what resource you have, like either like a data resource or computer resource you have. Given different resource, you will achieve a different level of improvement.
Thank you.
Should I answer read all of them and answer, right? Or what's
yeah, please, that'd be great.
Yeah. The second question is also another framework. The individual blocks chosen from defined set operator would optimizing their parameter size of the given improvement. Yes, I think I do believe it is like I didn't go through very so thoroughly, but we noticed optimize those hyperparameters at each like component operation level definitely give us benefit here. So in this work, the C2F NAS, this is after final stage. There's an additional stage we call compound scaling. Compound scaling, just like giving your searched architecture, trying to figure out what's the best combination of this like a kernel size or number of channels, and also like stride of all those parameters here, trying to figure out those like micro parameters here to achieve the better performance. Yes, that's definitely gonna help. And next question is, are there any advances to apply flavor learning when dealing with very heterogeneous client informatical heterogeneous client informatical indices segmentation? So by heterogeneous clients, you mean like there's a significant domain difference between different clients. So one way, just in my mind, because I tried in my work, so normally you can share only part of model. Like for example, you can use a common encoder and keep some part of the rest of the model as like unshared across different clients, and the decoder part would naturally like do the domain adaptation for you. Okay. Next question, do you consider self-supervised learning as some kind of unsupervised learning, or is more like semi-supervised learning? Which is learning method more promised for medical imaging application? This is another excellent question. So I would say that unsupervised learning is kind of a big concept. So self-supervised learning is one of it, and the semi-supervised learning is a part of it. So self-supervised learning is a very hard trend nowadays, not only in medical imaging, but also in computation. They're quite popular. People are trying to push this like the boundary of the self-supervised learning, especially for the contrastive learning, if you heard of the term. And also recently, I think from Facebook last year, they published a paper about the masked autoencoder to do the self-supervised learning, and you can, as they claim, it can benefit the downstream tasks. And also there's the work last year from Siemens. They're pre-trained their model on the 2 billion of the medical images, because those 2 billion including both 2D and 3D images. And in their downstream task is the classification and object detection. They show the clear advantage of using this model weight from the self-supervised learning. And for semi-supervised learning, it's kind of is another perspective to improve performance, because semi-supervised learning is still using the most popular one is like like a noisy student from Google. So you're still using the supervised task as a loss function objective. And I think they achieved a very good performance as well. Again, so which one was better? I think it's kind of depend on the balance of the data. So let's say you have like a big chunk of the label data and another like small chunk of unlabeled data. I think the semi-supervised in this context will work better. But if you have a like small chunk of the label data, but a huge chunk of the non-label data, I think even for semi-supervised learning, it's really hard for the model to figure out what's happening in this big chunk of unsupervised data, unannotated data. But really, like it depends on the ratio between the label data and non-label data. Any suggestion about future direction of using shape-wise DL models? Yeah, I think this is like this is a very interesting topic. There's different ways to define the shape-wise. As I see, like using like this kind of mesh or surface. You can define the shape. You can define the like mean shape of the object you want. But I saw other publication. I myself have publication. So you can use like a binary mask as a shape prior and use an encoder to extract the features from those like priors, from this like binary mask as a prior to help you for the segmentation. I think the future will be, it could be a combination of both, or I think the question is answered. So how to find the right space or good space for the priors.
Okay.
So
what is the email that you have sent in the
morning? It could be low dimension.
What is the email is about?
Okay. Next one is how can you check why architecture is not working in fair learning since you cannot see segmentation mask overlay on image? Oh, okay. So for architecture, so for our paper, we are doing a synthetic experiment, which means we have different machines, but machine still ours, so we can collect results there. But in real scenario, in real practice, the client can compute the validation or text accuracy on their end, and they can give you a number. The basic number is kind of a very important indicator to show like whether the model itself is working or not. Is there any problem? That's like a very limited information you have, but at least it's an indicator to show whether the architecture is working or not. Any other question?
Yeah, and we are just about the time. Yeah, and thank you so much, Dong, for giving such a wonderful talk, and thank you all for attending this talk. So this Mikai Industrial Talk is being held monthly. So looking forward to see you next month. Thank you.